Hello and welcome. My name is Thomas Onyango. I study under Dr. Ralph Rapp at Texas A&M in College Station. Today I will be talking about photon production from calcium 40 on calcium 40 collisions at 35 MeV per nucleon. First, a brief introduction. The objective of this project is to study the matter created in heavy ion collisions at Fermi energies using photons as a penetrating probe. Some questions we would like to answer with this project are: does the fireball in these collisions thermalize? And if so, how? Can thermal photons reveal the temperature evolution of the fireball? Can photons probe the nuclear interactions in the fireball? Is photon radiation sensitive to the isospin content? And can we learn about the asymmetry energy at high density? To answer these questions, we employ coarse graining on the output of our transport simulations of nuclear collisions. We can then extract local temperatures, densities, and collective properties from the output. We then convolute thermal photon rates over the space-time evolution of the extracted thermodynamics. We simulate central calcium on calcium collisions at 35 MeV per nucleon over 24,000 events using the constrained molecular dynamics transport model. To the right, you can see a schematic diagram of our collision system. Two nuclei coming in with this velocity. The coarse graining prescription that we use is to discretize space into cells of 2 Fermi cubed and time steps of 5 Fermi over C. Here is a representation of one of our cells, and you'll see that it's adjacent to the center of our collision and not encompassing it. This one cell is representative of the 8 cells that are adjacent to the center of the collision that we extract our data from. By performing coarse graining on the output of our transport model or transport calculations, we can obtain localized nucleon momentum distributions. We then extract chemical potential and temperature using Fermi fit functions based on those localized momentum distributions. From the distributions measured along the transverse direction, we see that the temperature increases from 3 MeV to 7 MeV. We also notice that the incoming kinetic energy dissipates into thermal energy at around 200 Fermi over C, which is representative of a 3-dimensional thermalization. As soon as this initial kinetic energy decreases or depletes, the temperature remains rather flat, it plateaus. Now to talk about our thermal photon spectra for this collision, we start by calculating the thermal photon production rate from nucleon Bremsstrahlung using empirical NP cross sections. This photon rate is written right here, and d pi is representative of the outgoing phase space. And I would like to bring attention to our energy momentum conserving delta function. We go beyond the soft photon approximation by conserving the energy of the photon. We do not conserve the momentum of the photon because it is negligible compared to the momenta of the involved nucleons. A Feynman diagram for our nucleon Bremsstrahlung process is shown right here. Once you have the photon rate, you can calculate its associated photon energy spectrum. We show the thermal photon energy spectrum using transverse thermodynamics. That would be this blue line. And we see that it underestimates the experimental data. Once we account for the initial motion of the nuclei, we see a substantial increase in the yield. And that would be this red line. This red line is still significantly higher than the data for a comparable collision system, but there are still further corrections we can make to bring down the overall yield, such as implementing isospin dependence, which would mean calculating the smaller NN and PP contributions, which should bring down our overall yield by a factor of 2. We can also implement realistic experimental constraints, such as centrality selection and geometric detector acceptance. There are also other corrections that we can make that I do not have time for in this presentation. So in conclusion, our process is to use transport code to simulate nuclear collisions. We perform coarse graining on the output of that transport code to get localized nucleon momentum distributions. We then model fit functions around the momentum distributions. We can then extract quasi-thermal parameters from those accurate fit functions And we use those quasi-thermal parameters to calculate thermal photon rates and multiplicities. From the distributions measured along the transverse direction, we see that temperature increases from 3 to 7 MeV. We also observe that the initial kinetic energy gradually dissipates all the way until 200 Fermi/C. And then we calculate that photon production from primordial and nucleon-nucleon collisions moving with centroid energy dominates over photon production from thermalized nuclear matter. The future plans for this project are to finish implementing off-equilibrium effects in the photon rate and multiplicities, to implement isospin dependence, which would mean calculating the contributions from NN and PP, and then to implement realistic experimental conditions, such as angular cuts based on detector placement. Thank you for your time.